So first of all, I would like to thank Jules Hoffmann for being with us today, giving a Humanitas lecture and starting a traditional meeting that we have each year on translational immunology. And Jules Hoffmann has made a seminal contribution in the general field of innate immunity, and as we will hear, the path to clinical benefit started a long time ago and far away from humans. And of course, he was awarded the Nobel Prize for Medicine. And Jules is visiting us for this meeting and is a visiting professor of Humanitas University. So my first question to you is, what are the key steps, the milestones in your personal history? I mean, personal in terms of science.
Of course. Let me say the first thing, we knew in the beginning that insects were very resistant to microorganisms, but we didn't understand the mechanisms. And the first steps came when we found that there was an inducible response, that the insects, flies, produced large amounts of antimicrobial peptides. And so we were not the only ones to find that. Hans Boman had also found molecules in Stockholm. And then came the situation that in the genes which we cloned, there were sites which had been reported in the mammalian system to be related to NF-kappa B activations. NF-kappa B at that time had just been discovered by David Baltimore. And then came the notion that flies could have an NF-kappa B family member. And so we, step by step, we moved forward. And it took long years to get to that. First of all, to get the identification of the inducible molecules, and then to be able to show that actually the NF-kappa B system, as it had been initially discovered in embryonic development, that was also used in the immune system, and then things built up, and then around the middle of the 90s things became clear. And then additionally we could show that many of these molecules were present in other systems. And then by the end of 2000, it was in between. Similar systems had been found in mammals, including in humans, specifically by Charlie Janeway and Russell Medvedev, and on one side, and by Bruce Beutel on the other side. And then the whole story became sort of clear, I should say, although it still is not totally clear, but that we had a system which has probably evolved about 1 billion years ago, and sort of a toolkit for fighting microbial infections. And that in this toolkit, the various groups have selected some of their tools, and not all groups use all the essential partners. But interestingly, everything which we find in a fly is present in sea anemones, and even in sea anemones and in sponges. There's more than in the fly, and they are closer to some extent to humans, because flies have dispensed with a certain number of the partners. So bottom line, that's the situation. Now, it's interesting to reflect that 95% of all species on Earth nowadays rely only on innate immunity to fight infections. And then in addition, among those, the vertebrates which have developed adaptive immunity, I'm told, and that was Rolf Zinkernagel who told us recently, 95% of our own defense relies on innate immunity. And it is only a restricted number of microbes which overcome the innate immune response, and they become pathogens. And those then are dispensed off by adaptive immunity.
Yeah. And it's a toll story. By toll, in German means extraordinary, wonderful, and it's actually the name of the gene.
Yes.
And in the vertebrates, the nomenclature we use is toll-like, so it's TLR. and that has moved to the clinic in terms of agonists and genetic risk and hopefully new perspective for vaccines. So this is a fantastic story of basic science, and you are the one who can comment on the importance of basic science.
Well, I would certainly like to say that what started our work was curiosity. It was not, we were not, at that time we couldn't imagine that the antimicrobial response of insects we worked on, started on grasshoppers, that they would have any sort of relevance for human health. That was, so my major problem in the beginning was to get funding for that topic and to convince people that it was of some interest. And some people say, well, maybe you'll find new insecticides, or find a way of inhibiting the antimicrobial defenses of insects. But then, step by step, it became clearer that once we had a certain number of very interesting antimicrobial peptides identified, then industry became interested in saying, particularly the plant chemists who said that could be of interest for our own applications to fight. And indeed, we did. That was with von Poulenc. We were able at a given moment to express genes for one of our peptides, Drosophila peptides, in plants which were infected with fungi, and they became resistant. And the very the very unfortunate thing is that at that time in France, like in other European countries, developed under the influence of Greenpeace, strong attitude against genetically modified plants. And that may change now, because now it appears that they call this not green but red plant technology, because you can now produce a certain number of very important molecules. Insulin has been shown already, but also coagulation factors can be produced in plants. And so probably they will come back to that situation one day also.
So it's a fantastic trip from curiosity to application.
Yes, which you can never foresee. You cannot. That's, we agree on that. So I often say when I'm asked that question occasionally, I say, I fully understand that we have to have applied science, we have to have researchers working on a very defined theme to improve this or that aspect. But then on the other hand, if we really stop doing unbiased research without exactly knowing where we go, then we'll take away much of the work which has changed our situation, which has changed medicine. And this is this former president of the Nobel Foundation said that 90% of the Nobel laureates, Nobel Prizes over the last 30 years were given to people who had not worked with an applied vision, but who had really asked fundamental questions and often spent 30, 40 years working.
Yeah. So this is the past, this is the present, and the future. And the future is relies on the young people. This is a university, and we're doing training. So I wonder whether you have a message for young fellows.
Yeah, I mean, what is important for every one of us in the beginning is to ask a good question and an interesting question, and to believe in the interest of the question. So, and a good supervisor would say, you must know about that aspect. And then for the rest, it's a matter of being very open-minded to other fields, of focusing, but not over-focusing on your own research. You have to, I mean, if I just look at what we have done, we started from zoology, went to cell biology, to molecular biology, always analytical chemistry, and then molecular genetics. So it has been continuous progress as science progressed. I mean, so we're benefiting from all the advances. So you have to keep an open mind on what is going on in other fields. And then, unfortunately, you have to work hard. And they have to know that you have to work hard. And on the more softer side, I often say...
No substitute for hard work.
I don't know. But it's not in the other fields, it's the same. I mean, if you're a butcher, my grandparents were butchers, the other side were farmers, and they had to work very hard. There was not a 35-hour week like in present-day France. It was not, but that's not for butcher eyes. Not for. And on the more pleasant side, I always say that what has been very helpful for me is to have had a very warm family life and to be a very good social life, and also to be interested in other aspects, literature and art and so on, not too narrow-minded. I think it's important for the equilibrium in science.
I fully agree. And well, thank you. Thank you very much for being with us and for being with us at Humanitas University.
Thank you for inviting me.
Thank you.